Mathematics is the study of numbers, and the classification of numbers is one of its foundational concepts. From the rational and irrational numbers taught in secondary school to the deeper realms of algebraic and transcendental numbers, these classifications not only reveal the essence of numbers, but also highlight the depth and complexity of mathematical exploration. In this video, we will start with the basic classification of numbers and, through key theorems and historical developments, delve into the fascinating world of algebraic and transcendental numbers in mathematics. Real numbers can be broadly divided into two categories: rational and irrational numbers. Rational numbers can be expressed as the ratio of two integers, in the form p/q, where p and q are integers and q not equal to 0. Examples of rational numbers include integers like -1, 0, and 7, as well as fractions like 1/3 and 8/3. Irrational numbers, on the other hand, are real numbers that cannot be expressed as the ratio of two integers. They are characterized by non-repeating, non-terminating decimal expansions. Familiar examples include square root of 2, square root of 3 pi, and e. Together, rational and irrational numbers make up the set of real numbers, but irrational numbers are far more intricate and mysterious than their rational counterparts. Algebraic numbers are an essential subset of real numbers, representing a further refinement in the classification of numbers in mathematics. An algebraic number is a number that can be a root of a polynomial equation with rational coefficients. In other words, if a complex number x satisfies an equation of the form, then this x is an algebraic number. All rational numbers are algebraic numbers. For example, the integer 5 is an algebraic number because it is the solution to the equation x minus 5 is equal to 0. The fraction 1/2 is an algebraic number because it satisfies the equation 2x minus 1 is equal to 0. Some irrational numbers are also algebraic numbers. For example, square root of 2 is an algebraic number because it satisfies the equation x squared minus 2 is equal to 0. The imaginary unit I is also an algebraic number because it is the solution to the equation x squared plus 1 is equal to 0. The operations of addition, subtraction, multiplication, and division on algebraic numbers still result in algebraic numbers. For example, square root of 2 plus square root of 5 is an algebraic number because both square root of 2 and square root of 5 are algebraic numbers. Complex numbers in the form a plus bi, where a, b are rational numbers and I is the imaginary unit, are also algebraic numbers. Although there are infinitely many algebraic numbers, their quantity is countably infinite. In contrast, the set of real numbers is uncountably infinite, which means the vast majority of numbers are not algebraic numbers. The opposite of algebraic numbers are transcendental numbers. These are numbers that cannot satisfy any polynomial equation with rational coefficients. Transcendental numbers are defined as those that do not belong to the set of algebraic numbers. In other words, they cannot be expressed as the roots of any polynomial with rational coefficients. The first example of a number proven to be transcendental was a Liouville number, constructed by the mathematician Joseph Liouville in 1844. These numbers take the form In 1873, Hermite proved that the base of the natural logarithm, e, is a transcendental number. In 1882, Lindemann proved that the mathematical pi is also transcendental. Although algebraic numbers are infinite, they make up only a small part of the real numbers. The vast majority of real numbers are transcendental, and the number of transcendental numbers is uncountably infinite. This means that if you randomly select a point on the number line, the probability of choosing an algebraic number is 0, while the probability of choosing a transcendental number is 100%. In other words, it is impossible to pick any algebraic number at random. In 1882, Lindemann and Weierstrass proved the Lindemann-Weierstrass theorem, which states the following. Through this theorem, many important numbers can be proven to be transcendental, such as pi, e to the pi power, natural logarithm 2, and so on. To prove that pi is transcendental, we need to use the famous Euler's formula. Little did the great Euler imagine that one of his formulas would contribute so significantly to the proof of a transcendental number more than 100 years later. If pi were an algebraic number, then I pi would also be an algebraic number. This equation can be written as d to the power of I pi plus e to the power of 0 equals 0. According to the Lindemann-Weierstrass theorem, this equation can only hold true if all the coefficients of e to the alpha power are 0, which contradicts the Lindemann-Weierstrass theorem. Therefore, pi cannot be an algebraic number. Similarly, we can prove that natural logarithm 2 is transcendental. This theorem also solves a problem that had puzzled mathematicians for thousands of years, a problem that challenged countless thinkers, the problem of squaring the circle. Imagine you have a circle and want to construct a square with exactly the same area, but you're only allowed to use a straight edge and a compass. How would you do it? This problem, though it seems simple, is actually extremely profound. As early as ancient Greece, mathematicians began to explore this problem. They attempted to find a solution through the properties of geometric figures and algebraic equations, but they were never successful. Why is this problem so difficult? The key lies in the tools we use for construction, a straight edge and a compass. While these tools are simple, their capabilities are limited. A straight edge can only draw straight lines, and a compass can only draw circles and measure distances. To precisely construct a square with the same area as a given circle using only these tools is nearly impossible. So, is there a way to bypass this dilemma? Mathematicians tried various methods, including using special curves to approximate the shape of the circle, but they were unsuccessful. It wasn't until the 19th century, when the French mathematician Lindemann proved that pi is a transcendental number, that the problem was definitively resolved. What does it mean that pi is transcendental? Simply put, it means that pi cannot be expressed as the ratio of two integers, nor can it be obtained through a finite number of additions, subtractions, multiplications, divisions, or root extractions. This property makes it impossible to represent the exact value of pi using algebraic numbers, and therefore impossible to construct a square with the same area as a given circle using a straight edge and compass. In 1900, Hilbert posed an important conjecture regarding transcendental numbers. If a and b are algebraic numbers, and a naught equals 0 and 1, while b is not a rational number, Is a to the power of b necessarily transcendental? This question was solved in 1934 by mathematicians Gödel and Schneider, who proved that the answer is affirmative. This result is known as the Gödel-Schneider theorem. Although mathematicians have proven that many numbers are transcendental, many questions remain unresolved. For example, is e plus pi or e minus pi transcendental? Is pi to the pi power or e to the e power transcendental? These questions are still waiting for mathematicians to explore.